fuel, as it were, is this 2-carbon acetyl group on CoA. Acetyl-CoA is the fuel. The output's 2 CO2s, an ATP, and electrons in the form of 3 NADHs and 1 FADH2. You may say, I lied. I promised you 30 ATP. So far, we've just made 1. Next lecture, we'll talk about how you convert the power of the electrons on these NADHs and FADHs into ATP. So the citric acid cycle in itself just generates the 1 by substrate level phosphorylation. You would think this would be a straightforward process. Maybe one enzyme could do it. It takes many enzymes in the cyclic pathway. This is just the first step where we make citrate. The 2 carbons, the acetyl function is highlighted. That pair of carbons gets put here on top of a 4-carbon acceptor molecule, oxaloacetate, 1, 2, 3, 4. Plus those 2, we make a 6-carbon tricarboxylic acid called citrate, hence the various names. It's a tricarboxylic acid, TCA cycle, tricarboxylic acid cycle. Sometimes it's called after the first intermediate, the citric acid cycle, because we make citrate. Sometimes after Sir Hans Krebs, the guy who figured this out. This is a strongly downhill reaction, negative 32 kilojoules per mole. So acetate flows into there to make citrate. And then we go around in a big circle. We do all these different reactions, some of which are oxidative in nature. So there's 1, 2, 3 places where electrons are donated, a pair of electrons get donated to NAD to NADH. There's a separate one where a pair of electrons are donated to FAD. There's this one place where you make ATP. Some organisms make GTP, some make ATP, but energetically it's equivalent. And there are 2 places where you decarboxylate. These are oxidative decarboxylation steps. You donate a pair of electrons and kick out a CO2. Donate a pair of electrons, kick out a CO2. So here's the carbon that comes in as an acetyl group. Eventually, as it goes through the cycle, you lose 2 carbons as CO2. And we're doing lots of oxidation. Here it is, just with the structures. If you're interested, just to see the structure.